All right, so we have two things left to talk about confidence intervals, and that is making a confidence interval for a percentile, like the median of a distribution or the 75th percentile of the distribution, very useful for demand planning and supply chain analytics, and then also a new procedure for coming up with a confidence interval called the bootstrap. So, very quickly, confidence intervals for percentiles. So, if we think about the percentiles of a distribution, what does that refer to? Well, it refers to a very particular value of x for any percentile that we have in mind. So, what we say is that when x is the 100th percentile of a distribution, that means that the probability of observing a value of x or less from that distribution is p. So this is best illustrated with a couple examples. Let's take the number of minutes that someone spends on a website before they eventually leave to be described by an exponential distribution with lambda of zero point 0.2, so that the average is at 5 minutes. So we might want to know something about the 25th percentile of this distribution. In other words, what's the 25th percentile of the length of time that people spend on this website? Well, the 25th percentile is going to be that time so that there's a 25% chance of observing a value of x or less from the distribution and a 75% chance of observing that value or more. So we've talked about percentiles and quantiles with our notorious zoo. Asking for the Q version of the function that describes the probability distribution in R gives us these percentiles. So if we ask for Q exp 0.25.2, that lets us know that the 25th percentile of the distribution is 1.44. So since 1.44 is the 25th percentile, there's a 25% chance that a time that we observe from this distribution will be 1.44 or something smaller, and a 75% chance of something being bigger than that value. The median is also known as the 50th percentile. If we throw that through the QEXP function, we get just about 3.5 minutes. So 50% chance the waiting time or the time on the website will be 3.5 minutes or something smaller. 50% chance that the time on the website will be 3.5 minutes or something larger. Now, where this relates to demand planning and supply chain analytics are those upper percentiles. Very often we'd like to know the 99th percentile, say, of a demand distribution, so that there's a 99% chance that you're going to be able to cover demand for a particular week. And if we run the 99th percentile through QEXP in this example, we get 23 minutes. So 23 minutes is the 99th percentile. That means there's a 99% chance that the number of minutes that someone spends on that website is going to be 23 minutes or something smaller, only a 1% chance that the time on the website is going to exceed that value. So sometimes when we sit down, collect some data, and want to talk about the probability distribution that's making the data, we're most interested in talking about the percentiles of that distribution, like the median or maybe the 99th percentile for demand planning. So why would we want to talk about percentiles just in general? Well, I think the most famous percentile is the median, that 50th percentile. And I think the median is particularly useful in business analytics just because we deal with very skewed distributions time and time again. So let's imagine we're dealing with a probability distribution that looks like this. It's rising up very quickly to a peak, then kind of taking its time to decay off towards larger and larger values. If we ask what's the average value of this distribution, well, that's given to us by this red line. And we see the red line, technically is the average of that distribution, the expected value, but it's kind of far away from where that peak is. I think if you would ask a lot of people to summarize this distribution, their eyes would hone right into where the peak was and say a typical value is right at around maybe 15 or so, kind of where the location of the peak is. So the mean, it's very sensitive to the entirety of the shape of the distribution. If we have a long right-handed tail, that mean is going to be dragged up towards that tail. And we might not think it serves as a great summary of the distribution as a whole. Now, the median is not as affected by the shape of a distribution, specifically skewness or outliers or anything like that. If we were to ask, well, what's the median value of this probability distribution, we get the blue line. And we see that's a little bit closer to the peak, and so that's a bit more acceptable to us. Ask someone on the street, hey, which is going to be the better summary of a typical value? And I think most of them would say the blue line, the median in this case. So if we're not really that interested in actually estimating the average of a probability distribution. Maybe because the data we've collected is very skewed, so the median would actually be a better summary of a typical value. Then we want to talk about confidence intervals or of percentiles. Or if we're doing demand planning, we might want to know a 95% confidence interval for a 90th percentile of the demand distribution. So how do we go about doing that? Well, let's imagine we've collected some data. Maybe these are the weekly demands that we've observed for a product over the course of a couple of years. And to help better with demand planning, we want to estimate the 85th percentile. So what is the value of the demand so that there's an 85% chance that the demand for that week is going to be that value or less, and a 15% chance that we're going to observe a demand that's larger than that value? How can we come up with a 95% confidence interval for this 85th percentile? We can kind of see it's maybe around 110, but what's a range of values that are plausible for this percentile based on the data that we've collected? So I'm really just going to skip to the very end of this discussion. It gets a little bit deep into the mathematics that we're really not all the most interested in, because I've written a very useful function that'll help us get an exact confidence interval for any percentile that we have in mind. With the one caveat being, we might not be able to specify what the confidence level is ahead of time. Let me illustrate that by looking up this function, this getCi for percentile, and reading it into the global environment so that we can actually use it. So, what does this function do? Well, the amazing thing about getting a confidence interval for the percentile is that our procedure doesn't care at all what the shape of the probability distribution is. It can be super skewed, it can be symmetric, it can be normal. It turns out that we have a procedure to get a confidence interval for any percentile that we want, the median, the 90th percentile, etc., without actually having any information about the probability generating distribution, even its shape. It's kind of remarkable. And the way that we're going to construct this confidence interval is by choosing two very specific values that we've observed. So we're going to sort those values from smallest up to largest, and we're going to run this getCi for percentile to let us know which two values should we take as the lower limit and the upper limit for that confidence interval. So for this particular example, well, we want a 95% confidence interval for this demand distribution. We don't know the PDF that's generating these weekly demands. We can tell the 85th percentile is right at around 111 or so. And so can we figure out a confidence interval based on the data that we've collected? Well, yes, we can, and it's going to be remarkably easy here. So let me find out where this data is. So we're going to have these demands be generated like this. Here's our demand distribution. And here's how we're going to use this getCi for percentile. So here's our demands. What we do is we say, let's get the confidence interval for this 85th percentile. The arguments, the only thing that we need in order to make this confidence interval is our sample size. So in this case, length of demands will let us know the number of demands we've observed, our sample size here. And then what we want is the percentile. We have to specify, okay, we want the 85th percentile. And so we'll put in 0.85 here. And this is all we actually need to do. Remarkably, this procedure doesn't care what the shape of the distribution looks like. It doesn't care what that probability distribution is. It lets us know that an exact 95.1% confidence interval is from Y298 to Y325. Now, what does that mean? The Y represents the sorted values of the data from smallest up to largest. So if we went and said sort demands, these are all the demands we've observed from smallest up to biggest. If we said, okay, well, what is the 298th smallest up to the 325th smallest demand, we get an interval that looks like this, 96 to 106. And that's our confidence interval. We can say that we're 95% confident that the 85th percentile of this distribution is between 96 and 106. This is the range of values for that 85th percentile that are plausible based on the data that we've collected. And this is just a very general procedure. So we didn't get exactly 95% confidence. It's pretty close, 95.1%, but that's just part of the price we pay for such a general procedure. And so that's as easy as it gets, really, for coming up with a confidence interval. We don't have to check any assumptions. We don't have to look at a histogram. We can just do it. What about a 95% confidence interval for the median value of this distribution? Well, just changing this up from 0.85 to zero point 0.5. The median is the 50th percentile. We know that we're 95.2% confident that the median is between y165 to y203. Well, what does that actually correspond to? Let's go and look. What is the 165th smallest value? What's the 203rd smallest value? We're 95% confident the median of this distribution is between 65 and 73. So, a very general procedure, and we know that when we talk about the confidence of a confidence interval, that talks about the probability that the procedure actually does generate a range of values that covers the true value of that unknown parameter. And so it's kind of nice that we get an exact value for what that confidence is with this procedure. Confidence interval for the value theta with the MLE. For mu, differences in mu's. Those are all approximate. So when we say, we have a 95% confidence interval for the difference in averages, that's really an approximate 95% confidence interval. Might be a little bit more, might be a little bit less. You never actually know what that achieved level of confidence is going to be. But this procedure tells you exactly what's the probability that the procedure ultimately ends up with an interval that covers the true percentile of that distribution. Easy as that. So when percentiles are what you want to estimate, well, go back to this set of lecture notes, get this R code right here, because this will give you that confidence interval with really minimal work. Now, I want to talk about a very general procedure, kind of a very different approach for coming up with a confidence interval for some parameter of a probability distribution that we want to estimate. So we've spent a good deal amount of time talking about ways of obtaining a 95% confidence interval for a few common quantities. If we want a 95% confidence interval for P, the probability of some event occurring, we run binom.test. That's a quick and easy way to do it. If we want a confidence interval for mu, well, we take the sample average and then move plus or minus some number of standard errors, usually right at about 2, away from it. So the standard error is that standard deviation over the square root of the sample size, S being the standard deviation of the data values we've collected, and we get an answer really quite quickly. If we want a confidence interval for the value theta here, the parameter of a probability distribution, well, we find that MLE and then go plus or minus 2 standard errors. We read those off of FitDist. So for P, for mu, for theta here, we actually have pretty well-established procedures for coming up with the confidence interval under the condition that we're dealing with a large enough sample. So we've talked about those sample size constraints. We need to have enough data for this procedure to be reliable. What if we don't have enough data? What if n, the sample size, is too small? Or what if it turns out that we're trying to estimate a different parameter of the probability distribution than what we've talked about? So what if we really want to know the standard deviation of the probability distribution? Or maybe the skewness or the interquartile range? Well, we don't know what the MLE is necessarily for what those parameters are, and so we're kind of left just twiddling our thumbs, not being quite sure over how we can produce a range of values that seem plausible for that unknown parameter based on the data that we've collected. How would we estimate the standard deviation of a probability distribution from the data that we've collected here? And so here comes the bootstrap, which is a very general procedure that is going to help us make not only confidence intervals for mu, the average, if we want it to, a percentile, if we want it to, theta, the parameter of a probability distribution, if we want it to, but almost every other parameter of a probability distribution that we might want to look at. And on top of that, there's really no math involved. The bootstrap provides a nice math and equation-free context of coming up with the confidence interval, but it does come with one major caveat. So when we typically come up with a confidence interval, we choose 95% confidence. And the bootstrap, it's going to get kind of close to 95%, but it might be a little bit above, and usually actually is a little bit below 95%. So we're going to introduce a procedure that in theory sounds good, and in theory should produce a 95% confidence interval. But what we're going to find is that the achieved level of confidence how often our procedure actually produces a range of values that covers the true value, that unknown parameter. It's usually a little bit less than that 95% target here. But for such a flexible procedure, it's kind of a small price to pay. We might want it to be 95% confidence, but it might end up being something like 90 or so. So you'll see what I mean as we work through this. All right, so what is this bootstrap? Well, the bootstrap is a way where we can glimpse the sampling distribution of the statistic that we're using to estimate the unknown parameter of the probability distribution. So remember what a sampling distribution is. It's the possible values for that statistic that we might measure when we go and collect data. And we talked about the sampling distribution at length when we introduced that central limit theorem demo. We know that if we fire up the random number generator and take a random sample from some probability distribution, well, I'm going to get a different set of data values than what you do. You're going to get a different set of data values than your friend. There's a lot of different potential ways that we can end up with a collection of sample values. And so what the sampling distribution of a statistic is all about is, well, what are the possible values of that statistic that you might measure when you, me, your friends go and collect data from this probability distribution? So we've played around with this before. If we imagine that, hey, here's the PMF of the probability distribution that's making our data. All of us, if we go collect the data from this, we'll get a different mixture of zeros, ones, twos, threes, etc. If we go and calculate our sample average, we're all going to measure a slightly different value because all of our samples are slightly different. If we look at the distribution of possible sample averages, though, that we might measure, that central limit theorem said that, hey, as long as you're dealing with a large enough sample, the distribution of those possible sample averages is actually quite predictable. In fact, it looks very much like a normal curve, and not only any normal curve, but a normal curve whose peak and whose standard deviation here you can actually anticipate from the probability distribution itself. The key fact was, though, is that regardless of what this probability distribution was, we always ended up in the same place. The distribution of the possible sample averages that we might measure is always well described by some normal distribution. So if I were to change this up a little bit, change what the probability distribution that's making the data looks like, it's a slightly different normal curve in each case, but it's always a normal curve that's doing a great job at describing the possible sample averages that people might measure when they go and collect data. So why was this useful? Well, when we go collect data, we have exactly one sample. We've only measured exactly one sample average. We wanted to answer the question, how far off might our sample average be from mu? How far is our statistic away from the truth? The central limit theorem telling us that, okay, well, the sample average is never that far away from mu here. In fact, you can predict with some probabilistic certainty how far mu is away from the one sample average that you've measured. You can turn that into a confidence interval. So that's the key thing here. If we can anticipate how far off the value of our statistic is, what we're using to estimate that unknown parameter, we can leverage that into a confidence interval if we're clever enough. And that's what the bootstrap is after. The bootstrap is trying to provide us an alternative way for guessing what the sampling distribution is of our statistic. Basically, if we're trying to estimate mu here from a sample, it would allow us to glimpse, or at least guess, how far our one sample average might be, how far it is away from mu here. Once we get that, we can convert that into a confidence interval. So here's the crazy idea that's behind the bootstrap. The bootstrap says, okay, I really want to know the sampling distribution of some statistic. What are the possible values of the sample average that I might end up measuring when I go and collect data? But the problem is I only have one sample. So how could I possibly glimpse essentially what other values I could have measured for the sample average if the data turned out just a little bit different? Well, here's what the bootstrap does. Crazy idea, but it says, okay, well, sure, you're restricted to your one sample, but why don't we kind of glimpse a way the data could have turned out differently, kind of glimpse an alternative sample just by reusing the data that we've collected in a very particular way. Why don't we just put all the data values that we've collected into a big old bag and then create a new sample, an alternative sample, by reaching down into that bag, picking one at random, put it back, pick out another one with replacement essentially, and keep picking values out from that bag until we've made a sample as big as the size of the original data. So, for instance, maybe the original data values that we collected in our sample are 1, 3, 5, 9, 9, and 12. Well, a Bootstrap sample would say, okay, well, let's put these numbers in the bag. Let's reach down in that bag. Let's pick one out. Maybe we pick a 5 out first. We'll put it back. We'll reach down into the bag again, draw out another value. Maybe it's a 1. And we'll keep doing that until we generate a sample of the same size as the first one. So our second or our first alternative sample here might be the values 5, 1, 12, 5, 3, 1. There's only one 1 in our original sample, but we happen to pick 1 twice in our alternative sample. There's only one 5, but we ended up picking it twice. There were 2 9s in the original sample. We ended up not picking that in our alternative sample here. So that's plausible for, the way the data could have turned out if things worked out just a little bit different. And so we could go and actually repeat that procedure. We could create another alternative sample in the same regard. So you could generate this kind of in R really quite quickly. If we think about it, if we had, say, an original data set with 6 values, we have 6 choices for the first, 6 choices for the second, 6 choices for the third, a total of 6 to the 6, or about 46,000 different possible alternative samples that could be generated. And if we just generate a whole bunch of them, measure the sample average for each, that at least provides a glimpse as to how the sample average might have turned out to be if the data collection process turned out just slightly different. It gives us a glimpse at the sampling distribution of the sample average. So here's the original data. We can use the sample command, just using as our first argument the list of values we're allowed to pick. Sample x replace equals true. It'll automatically generate a sample exact same size as x, just picking each value with replacement. Here's one where the 9s kind of appeared a lot. We have 9s, 3s, and 12s. We happen not to pick 1 or 5 in this case. But you can see it's pretty trivial to create alternative samples here. Here's one that's just 3s and 5s. And so here's this crazy idea. Bootstrap says, okay, we'd like to know the sampling distribution of the statistic. We'd like to know how the sample average might have turned out differently if we had a different set of data values. So let's just kind of create these alternative samples, these alternative universe samples, and calculate the average on each one of those. Maybe that's a reasonable way of glimpsing the sampling distribution of the sample average. So let's kind of check it out. So let's create a vector, say called possible means, and go and create 10,000 different of these alternative samples. So sample x replace equals true, store that into x.alt, and then store into the ith element of possible means the average of that alternative sample. Well, what ends up happening? Kind of check this out. If we go make a histogram of all of those averages of those alternative samples, look what ends up appearing. We see something that looks like a normal curve, just as what the central limit theorem suggested that we were going to see. But we're glimpsing the shape without knowing really anything about that central limit theorem. It just kind of arises naturally and kind of justifies that, hey, this might be a reasonable way to actually glimpse the sampling distribution of the sample average here. If we use as kind of our best guess how far off x bar might be from mu from our original sample, just the standard deviation of these possible averages as we're doing the bootstrap, could that be a reasonable estimate of the standard error? We've talked about the formula for the standard error is just the standard deviation of the original data values over the square root of the sample size. Could this be another way that we could estimate the standard error directly? Basically, typically, how far off are the calculated values of, say, x bar on these alternative samples from the average of the data values in the original sample? Is that a legitimate thing to do? And the answer here is, yeah, it kind of is, and this procedure really works quite well in general. So let's run with that. If we take the standard deviation of our bootstrap estimates as our best guess for the standard error, we get an idea for how far off x bar might be from mu. And if we go and just look at the distribution of all of the possible sample averages that we measured over the course of doing this bootstrap, and just look at the 2.5th through 79.5th percentiles, well, the percentage of the possible samples that we generated that live between these two values here is 95%. So between the 2.5th and 97.5th percentiles, 95% of values live. So why don't we actually just treat that as a 95% confidence interval? Let's dive through all of those alternative samples that we generated, all those possible sample averages that we measured on those Bootstrap samples. Let's just get the 2.5th, 97.5th percentiles and call it a day. Why don't we say that's our 95% confidence interval? So, all right, that sounds like a reasonable thing to do. Does that actually hold water? So let's work with this with an actual example here. Let's imagine that we have a random sample of size 15, pretty small sample here, from a Poisson distribution. And so we can check our answer, let's take the value of lambda for this Poisson to be equal to 3. I would like to know, does this bootstrap procedure actually provide a confidence interval with 95% confidence? In other words, does 95% of the time I implement this procedure, do I get an interval that gets it correct, that covers lambda equal to 3 here? So let's try this out. Let's just do some programming. Let's just do this on our own here. So what we're going to do is just define lambda to be equal to 3. And I'm going to define my data vector, my random sample, to just be our Poisson, a random sample from a Poisson distribution. We're taking 15 data points from here with the value of lambda equal to 3. So lambda equals lambda. We already just defined it to be equal to 3. There we go. So here's the data values that I've collected. And we know that the lambda parameter has an MLE of just the sample average. So if I ask for the average value of my sample, this is the MLE for lambda, 3.2. So we know the MLE is an unbiased estimator in this case. Sometimes it comes back a little bit too high with a given sample, sometimes a little bit too low, but on average it gets it just right. 3.2 looks to be fairly close to the true value of lambda in this case by design, close to 3. What if we made a 95% confidence interval for this? Well, there's two ways of doing it. If we loaded up the fitdist plus library, we could fit the data to a Poisson distribution. We could do fitdist. And when we do that, if we get a summary, we get that the estimate is 3.2, like what we discovered here, with a standard error, kind of a guess for how far off our MLE is from the truth of about 0.462. So if we take the fit $ estimate and then go plus or minus 2 standard errors, that's the fit $SD component, that's our 95% confidence interval between 2.3 and 4.1. Well, this confidence interval got it right, so thumbs up for the Bootstrap for right now. But when we talk about 95% confidence, that just means that the procedure, especially this Bootstrap, needs to produce this interval that does get it right 95% of the time. So what if we generated a different random sample? Well, I'm going to reorder some of these commands. We don't need some of these commands anymore. Get rid of those. What if we generate a different random sample and see its confidence interval? That contains 3. That contains 3. That contains 3. All right, looks good. So 95% of the time, our procedure should produce an interval that covers 3. And it looks like every one so far is doing its job. Sometimes it's going to miss it. Sometimes most of the time it won't. 95% of the time it won't. So let's actually see, well, what is the achieved level of confidence here? What fraction of the time do we actually end up with an interval that ends up covering the true value of lambda, which we know is 3? So we know the MLE, when we say 95% confidence, we kind of mean 95% confidence. This procedure is pretty accurate. So why don't we go and define counter to be equal to 0 and just write a for loop to go through, say, 100,000 of these different random samples and check to see if we end up getting a confidence interval that covers 3. So if we have that the interval, when we run this, interval is going to become a vector of 2 values. So if that's less than 3 and 3 is less than the upper end point of the confidence interval, then we're going to bump up the value of the counter. So our confidence interval got it right. And so we'll look to see, well, what's the value of this counter after our simulation is run? So we're going through 100,000 different random samples. We're designing a confidence interval with allegedly 95% confidence. That's our target here. Well, what's the achieved level of confidence? Well, that'll be the fraction of time when I actually do have a confidence interval that covers 3 here. And so I was ambitious. 100,000 is actually quite a large number of samples to go through. So we're going to do the magic pause button, and we'll come back once the simulation's done. Well, I got impatient, and I quit the loop out a little bit early. We got through 88,919 different random samples, and so if we just divide the value of counter right now by I, that number, that'll let us know the achieved level of confidence of our MLE procedure. Bam, right at 95%, kind of as expected, that 95% confidence when we make that confidence interval for theta here using the MLE, the achieved level of confidence is usually pretty darn close to 95%. Now, what about that crazy bootstrap procedure? What is going to be the achieved level of confidence of this bootstrap? So let's go through and with the very similar for loop, I'm going to be a little bit less ambitious and go with just 1,000 different random samples. We'll generate our random sample. Then what we'll say is, okay, well, let's get the bootstrap confidence interval. What we'll do is go and make our bootstrap samples. Let's make 499 of them. That sounds like a great number here. And then we'll determine the percentiles of that bootstrap sample, the 2.5th and the 97.5th, and then we'll use the range of values there as our confidence interval. So what we can do is say, put in a vector called boot means. We'll initialize that to be 0, 499 of those, and then we'll write a for loop that says, okay, for boots in 1 to 499, let's create an alternative sample where we just sample from the original values with replacements, and then put into boot means here the value of the sample average on that alternative sample. Bootstrap says, okay, you want to glimpse the sampling distribution? Lift yourself up by your own bootstraps and make those new alternative samples yourself. Just sample with replacement from the data that you have. And then once that's done, the interval here is going to be the percentiles of the values in boot means from 0.025 to 0.975, the 2.5th to 97.5th percentile. So for this, here's our original data values right here. We go through create all those bootstrap samples, 490 of them specifically. We look at boot.means. Here are the sample averages for each of those. Let's get the 2.5th and the 97.5th percentiles. That's our bootstrap confidence interval. Got it right in this case. So does it get right 95% of the time? Well, let's run our whole code here, and let's find out what is the achieved level of confidence of this crazy bootstrap procedure. And here's that warning that I was telling you about at the beginning of this unit. By design, we're coming up with a 95% confidence interval. That's our target level of confidence at least. We've designed it so that in theory it should have 95% confidence. But this procedure ends up falling a little bit short of that. Instead of 95% of the time having the procedure cover 3, the true value of lambda in this case, it's really only covering it about 90% of the time. So here's both the power and the drawback of this bootstrap procedure. The power is we didn't have to really do any math. We didn't have to know where the data was really coming from. We just needed to come up with, what's a reasonable statistic for measuring what we're trying to estimate here, the mean in this case. And we're able to guess or infer what the sampling distribution was of that statistic by making these bootstrap samples. So the power of it is, any statistic, any parameter of a probability distribution we can come up with, as long as we can come up with a statistic that reasonably estimates that, well, we're in business. We can come up with a confidence interval. So percentiles, standard deviations, interquartile ranges, anything like that. Hey, if I wanted a estimate of the standard deviation of a Poisson distribution, all I have to do is do boot SDs, kind of come up with a new name for it, and instead of measuring the mean for each sample, measure the standard deviation. This would actually give us a 95% confidence interval for the standard deviation of the Poisson distribution. In this case, I happen to know it. Me and the Poisson go way back. The standard deviation when lambda is equal to 3 is just the square root of 3. But you'll see, just kind of switching this up very quickly, now trying to estimate the standard deviation of this probability distribution with the standard deviation of our sample. Well, 80% confident. We tried to get 95%, we're falling a little bit short, and that's just one of the drawbacks here. So it worked for pretty much anything, but unless you have a fairly large sample, 15 is not all that large, then the achieved level of confidence might fall a bit short here. So that's what the Bootstrap is all about, and that's pretty much the main key point that I want you to take with you with this Bootstrap confidence procedure here. It's very flexible because we can bootstrap pretty much any parameter of a probability distribution. We can come up with a statistic that reasonably estimates it, but in reality, it's going to achieve a level of confidence that's a little bit less than the target. But I have an improvement. I'll talk about that improvement in a second here. So let me kind of officially talk about what this procedure is. Kind of let's write down in the bullet points, official bullet points here. What is this Bootstrap? Turns out there's a lot of flavors of the Bootstrap. So I've been discussing the percentile Bootstrap here, where if we want a 95% confidence interval for some parameter of a probability distribution, whether or not it's theta, mu, the standard deviation, the interquartile range, a percentile, almost anything under the sun, what we'll do is we'll generate a large number of Bootstrap samples, at least 499 of them, just by sampling with replacement from the data that we've already collected. So we'll find the value of the statistic, the estimator on each of those alternative samples, and we'll use that and refer to that as our Bootstrap estimates. The percentile Bootstrap says, all right, well, just go ahead and look at the percentiles of your Bootstrap estimates. If you want a 100 times 1 minus alpha percent confidence interval, go and look at the 100 alpha over 2 and 100 1 minus alpha over 2 percentiles of those Bootstrap estimates. 95% confidence, 2.5th to 97.5th percentiles. If you want an estimate of the standard error, how far off the value that you measured in your original sample, that estimator, how far that was away from the truth, you can just look at the standard deviation of the Bootstrap estimates to come up with a guess. So we can program this really not all that bad in R. There's going to be a package called boot that'll help us out, but let's just go through a few examples here. And we'll do programming live. That's always fun. So I'm going to load up the reg class library, and I'm going to load up a really old data set at this point. Back in the day, it used to be state of the art. 2011, we asked all the Stat 201 students, hey, what's the fastest that you've ever driven? And so looking at the distribution of this quantity, we see that some Stat 201 students have driven really fast. At least this is what they claim, at least. Over 150, all the way up close to the 200s here, and some really haven't driven all that fast in a car on their own. So we'll assume that all of these data values are valid. They're arising from some probability distribution. We don't really know what it is. And we'd like to estimate the average of this probability distribution. Okay, well, we know t-test, that's kind of the playground for when we're trying to estimate averages. So we could just say, hey, t-test, tell us what the answer is. In this case, we have we have a lot of observations, 627 observations. So even though this is a little bit skewed, that definitely meets the large enough sample size condition. We're 95% confident that the average top speed that people have driven, whatever this probability distribution is, its average, is between 101 and 103.8. So how does the Bootstrap compare to that? Well, let's go through the procedure again. So I'm going to create a vector just called bootmeans, and I'm going to make 4,999 Bootstrap samples. And so I'm going to name my looping variable boots, and we'll go through 4,999 iterations. In each iteration, I'm going to generate an alternative sample by sampling with replacement from my original data. So sampling from the values in the fastest speed with replace equals to true. And then I'm just going to record the bootstrap, or the mean of that bootstrap sample. So I'll take the average of that alternative sample here. And just like that, I've made 4,999 bootstrap samples. I can look at the distribution of those 4,999 values. Notice how much like a normal curve this looks. The central limit theorem says, hey, the sampling distribution of the sample average for such a large sample is going to look very much like a normal curve. And yeah, we kind of confirm that with the bootstrapping. If I want a 95% confidence interval using the percentile bootstrap, well, I just have to ask for the quantile of these boot means. 95% would be 0.025 to 0.975. And you know what? I sort of removed that missing value. I saw this NA and I was like, oh, we can get away with it. Let's actually go and do X orig. Is these values the ones that are complete? So if I get X orig, here are all the values with all the NAs removed. If I look at a summary of X orig, there we go. No missing values, so we're good. So now we'll sample from those original values with replacement, and we won't run into that weird issue. So Bootstrap says 95% confident that the average of this probability distribution generating the fastest speeds of these students is between 101 and 104 about. T-test says pretty much the same thing, 101 to 104, not that much of a difference. Cool thing is that we didn't have to know about t-test to actually come up with this confidence interval. With such a large sample, the Bootstrap's pretty valid here. And so this is pretty general. If I wanted to ask a different question, like, okay, well, that's cool. I know something about the average here. But what about the interquartile range of this distribution? The difference between the 75th and the 25th percentile. So what does that really correspond to? IQR. If I make a box plot of the values I've collected, this is the interquartile range, the height of this box here. So that's the way the box plot's drawn. So I'd like to know, okay, the probability distribution that's making this data, what's the 75th percentile? What's the 25th percentile? What's the difference between those two numbers? I have no idea how to estimate that using math, but I can estimate that with the Bootstrap so easily. Watch this. So instead of boot.means, I'm going to call it boot IQRs, just to make it very clear that, hey, I'm estimating the interquartile range right now. Nothing else changes except for what I'm measuring from each of the samples. So I'm still making my Bootstrap samples here. I'm just asking for the interquartile range of each of these samples. So run it, quantile it, not boot means, but boot IQRs. And I can say that I'm 95% confident that the interquartile range of the probability distribution that's making this data is between 20 and 20. Now, it's a little bit awkward because normally they're not the exact same number, but it's essentially saying that we've nailed it down. The data that we've collected, so extensive, so large enough that we know what that interquartile range is of this probability distribution. It's 20, give or take a tiny amount here. No idea how to get that with the math, but with the Bootstrap, very easy. So that's our one example here, if we wanted to write that just kind of by hand. Now, let's talk about a way to improve. Actually, let's do one more example. No, I'm going to save that example until Wednesday class, or if you're in the Tuesday, Thursday class, that class as well. What if we wanted to come up with a Bootstrap estimate of the slope of a regression? It's kind of a cool question here. If I wanted to quantify the relationship between the number of wins of an NFL team over a season and the number of fumbles that they've made, well, what does that relationship look like? Obviously, the more fumbles you make, the fewer wins you're probably going to have. How can we come up with a confidence interval for what that relationship looks like? If two teams differ in fumbles by 1 over the course of the season, what's a 95% confidence interval for the difference in the number of wins they might observe? So stay tuned for that. Okay, so this percentile bootstrap method, really cool, kind of bizarre, crazy idea, but it works in practice. This still has some shortcomings, and the biggest shortcoming is that the achieved level of confidence is usually a bit lower than the target level. We're getting the 2.5th to 97.5th percentiles in the hope that we're getting a 95% confidence interval, but in reality, if we go and check this, it turns out to usually have a little bit less confidence than what we designed it. So we want to improve on that. Obviously, people fell in love with the Bootstrap when it was first introduced, and they said, okay, how can we correct for this shortcoming? How can we improve this procedure so that the achieved level of confidence really is that 95% that we want it to be? And so to overcome this shortcoming, people invented quite a few tweaks to the original percentile method. And the one that I want to talk about is called the bias corrected and accelerated method. Now, the math behind this and exactly how it adjusts the bootstrap samples is quite a bit beyond the scope of this course. This is like PhD level stuff. The nice thing is that this is implemented in R so that we can actually use it. We can get these BCA, these bias corrected and accelerated confidence intervals, without really too much extra work here. We just have to learn how the boot package works and how to set that up. So we have ways for correcting for some of that shortcoming of the percentile bootstrap method. How do we go about implementing that? Well, we have to learn how to work with package boot. So chances are you haven't installed the boot package yet. So if you haven't installed that, install.packages boot is going to get you there. And once that's installed, we only have to do that once. But after it's installed, we always have to do library boot to load it in and to allow its full functionality. So how does boot work? All right, so boot is going to be the name of the function that we're going to run to essentially do all the bootstrapping for us, to create those bootstrap samples and to calculate the value of some statistic like the average, interquartile range, the standard deviation on each. It's going to take 3 arguments. 2 of the 3, very, very easy. The first argument is always the original data values. The last argument, R, tells us the number of bootstrap samples, like 499. 5,000, whatever number we want. The thing that we need to focus in on is this estimator argument, and that's essentially what we're going to tell the boot command to measure from each one of these bootstrap samples. So how do we do this? Well, writing this function is actually pretty easy. The key thing is that whenever we refer to the bootstrap sample in our calculation, we need to always, instead of just writing the vector x, like what we're used to saying is storing our data, as x bracket indices, and you'll be fine. So what do I mean by that? Just a few examples. If I wanted to run boot and estimate mu for a probability distribution, the average, here's how I would set up the estimator function. That no matter what I'm estimating, it's always going to look like this: estimator left arrow function x comma indices. It always starts out like this. It's only what's inside the curly brackets that's going to change from scenario to scenario here. So if I want to estimate mu, and I'm going to use the sample average as that estimate, well, what do I need to calculate for each bootstrap sample? I need to calculate the mean of x, but x bracket indices. This indices is just an argument that's there to make the function work. It's essentially letting you know what values from the original data end up in your bootstrap sample. All that goes behind the scenes. We just have to worry about actually writing it in a way that boot understands. We're trying to estimate the median of our probability distribution, and we're using the median of the sample as our best guess. Well, what do we need to measure for each bootstrap sample? We need to measure the median of the values, so the median of x bracket indices. If we want to be estimating, say, a percentile or a quantile of a probability distribution, well, how do we set up estimator? We actually don't need this PERC. That's kind of a relic of an older set of notes here. Still just x comma indices, but what are we going to use as our best guess? Well, the quantile of the bootstrap sample. So quantile of x with a particular percentile that we have in mind. So second argument of quantile is always that percentile that we want, but instead of x, we write x bracket indices. If we're doing the MLE, well, we have to make sure fit dist or plus is uploaded, but we would run fit dist. The first argument is always our data vector. We write it as x bracket indices. The name of the notorious distribution, $estimate, spits out the MLE here. So very easy to do that. And then once you've done that, easy to get the bootstrap confidence intervals out by running the command boot.ci. You can say type equals perc for the percentile. You can say type equals BCA for the bias corrected and accelerated, which is usually what we want. And it's really nice and easy to do that. So let me show an example. Let's go and actually just look at the fastest speeds once again. So we have our original data values right here. No missing values or anything. How would I get a BCA confidence interval for the average of the probability distribution that's making the data? Well, here's how I would do it. I need to define that estimator function. So it's always starting out as estimator, left arrow function x comma indices. And then I think, what do I need to measure for each of these bootstrap samples? Well, I need to measure the sample average. So I'll say mean of x bracket indices. It's always x bracket indices as we write this function. That's what we're going to do. Then I'm going to left arrow into boot in all caps, the result of running the boot command. So I'll actually want to make sure that library boot is up and running. The first argument is always going to be the original data. The second argument is going to be estimator, that function that we just defined. The third argument is going to be the number of bootstraps. 499, let's just do it. Done. Boot.ci on boot, and we just say, well, what type do we want? Do we want the percentile? Do we want BCA? Do we want both? Here's how you can do both. Well, that's a little awkward. Let's try that again. Sometimes the BCA, for some reason I haven't quite identified, doesn't work. So here's the percentile method. For some reason, still unknown to me, it wasn't able to implement that BCA correction. Let's try that with a different estimator here. Let's imagine we were trying to estimate the standard deviation of the probability distribution making the data. Well, what do we estimate from each bootstrap sample? Well, the standard deviation. And so what if we ran this? 95% confident that the standard deviation of this probability distribution is between 16 and 19.75. If I ask for BCA, do I get it? No. So there you have it. Sometimes R fails you and it won't give you the BCA confidence interval. Other times it'll work just fine. And for the homework, I've confirmed that BCA works just fine. Through these notes, actually, there's quite a few examples where the BCA does actually work just fine as well. So a little bit unsure exactly why the BCA method failed for that example, but it works for the other examples that you find in the notes. Okay, so let's sum up the discussion about the Bootstrap procedure. There's a bunch of additional examples for estimating different things. Great to have as a reference here. But let's sum up and talk about when we should use the Bootstrap, what are its pros and what are its cons. So number one, when we're doing this Bootstrap procedure, you don't have to worry about overkill with the number of Bootstrap samples you're creating. You actually don't really need more than a few hundred, and that's why I've been choosing 499. That's what I've seen recommended by other authors, and 499 is typically sufficient. Yeah, you can always make more. It's not going to hurt the procedure. Just might make it take a little bit longer to run, but you don't need to have like thousands upon thousands of Bootstrap samples. Another thing to look at is the distribution of those Bootstrap estimates. So that BCA method that I was mentioning really comes into play when you look at the distribution of the Bootstrap estimates and you see a lot of skew. Let me just show you an example of that here. Let's try to estimate the confidence interval, or estimate the 75th percentile of some probability distribution. So here's my original data values. I happen to know they're coming from a normal distribution, so that's cool. Here's my estimator that goes and gets the 75th percentile of each of those Bootstrap samples. I go and I ask for the percentile in the BCA methods, so I get them out. A good thing to do is always to look at the histogram of the Bootstrap estimates. What were those 75th percentiles on each of those Bootstrap samples? When you look at that, if you see a good amount of skewness, that's definitely nudging you towards, hey, you should probably use the BCA method here instead of the vanilla percentile method. So sometimes the percentile method, how we introduce the Bootstrap, is perfectly acceptable. And that's usually when the distribution of those Bootstrap estimates are roughly symmetric. We see skewness that's saying, hey, you should probably use that BCA method instead here. So don't need that many bootstraps. BCA definitely necessary if the distribution of your bootstrap estimates is relatively skewed. Otherwise, percentile is just fine. And just as an FYI, don't let all of our previous discussion be for nothing. If you actually know that probability distribution that's making your data, or let's say you can measure the MLE, or you're making an inference about averages and you have a large sample, use all of these results that people built up over the decades that are very reliant on statistical and probability theory. It's good stuff. That theory really carries us really quite far. The bootstrap is fantastic because it's so flexible and allows us to estimate pretty much anything that we want. But if what you want to estimate is already covered by the theory that we know, use the theory instead. Almost always, the theory is going to get you to a better confidence interval than what the bootstrap is going to provide you. But it is a lingering question and a matter of debate on, do we actually really need all that theory anymore? People have corrected and improved the bootstrap to a point where the confidence intervals that come out of this bootstrap procedure are actually pretty darn good. So can we just always bootstrap here? That allows us to avoid a lot of math. We saw how much math went into getting the MLE and its standard error. We had to do derivatives. We had to calculate expectations. That's a lot of math. Sometimes that's really difficult. The bootstrap is pure programming. Without any math, we just write a for loop, and we're pretty much done here. And it turns out that if we do have a large enough sample, yeah, you can kind of almost always get away with bootstrapping, except for a few very rare, very corner cases here. So there's a few things the bootstrap just isn't going to do a good job at estimating. So like if we had data coming from a uniform distribution between 0 and some unknown upper bound, Bootstrap is not going to give you a good confidence interval for that upper bound. Remember with the MLE, we had to use logic, actually, instead of using calculus and math to figure out what the MLE was. Stuff like that's always going to throw a wrench into things. Bootstrap's not going to work for that example. A few other really corner cases where it doesn't work either. But if you do have a large sample, you almost always can get away with the Bootstrap, especially that BCA method. If you're dealing with kind of a weird statistic that has a very skewed sampling distribution, the BCA method's got you covered, and it really does provide a procedure that achieves pretty close to 95% confidence. So, with a little bit of hesitation, yes, I can say that you can pretty much get away always bootstrapping as long as your original data values or original sample was fairly large. But I'm still going to encourage you not to forget theory. Most of your bosses that you'll run into took statistics, took probability before bootstrapping was a thing. They haven't heard of this, and so they kind of expect you to know the t-test. They expect you to know how to make confidence intervals for proportions and difference in proportions and averages and differences in averages and percentiles, all those good things, regression coefficients, etc., using the classic techniques. So still have that in your back pocket, still have that as a tool in your arsenal, but be aware that if you run into something pretty difficult that you're not quite sure what to do, you can probably get away with that bootstrap.